Good morning, everyone. My name is Dr.D.Ahima Emilet. I am working as an assistant professor in the Department of Mathematics, Faculty of Arts and Science, Bharat Institute of Higher Education and Research. Today, the topic of my lecture is about random experiments and sample space. This is a topic from the course named Probability and Random Variables. So, this is the syllabus for this particular topic. So random experiments and sample space, we'll be seeing about the first unit in this lecture. Now we'll move to the introduction to the probability theory. So Grambler's dispute in 1654 led to the creation of a mathematical theory of probability by two famous French mathematicians named Pascal and Fermat. So the fundamental principles of probability theory was formulated by Pascal and Fermat for the first time. After an extensive research, Laplace published his work in 1812 and laid foundation to this probability theory. So in statistics, the Bayesian interpretation of probability was developed mainly by Laplace. So the topic of probability is seen in many of the real-time world. So from its origin as a method of studying gains, probability has evolved in a powerful and widely applicable branch of mathematics. The uses of probability range from determination of life insurance premium to the prediction of election outcomes, the description of the behavior of molecules in a gas, and likewise, we have many applications. So its utility is one good reason why the study of probability has found its way into a textbook. Okay, so the interpretation of the word probability involves the synonyms such as chance, possible, probably, likely, odds, uncertainty, prevalence, risk, expectancy, etc. So our entire world is filled with uncertainty, and we make decisions affected by uncertainty virtually every day. So in order to measure this uncertainty, we turn to a branch of mathematics called the theory of probability. So let me give a small definition of probability. So probability is a measure of the likeness that an event will occur. So there are two different types of experiment. So one will be the deterministic experiment and the other one is a random experiment. Okay, so a deterministic experiment is nothing but say for example a genetic determination. Okay, and hitting a target is said to be a random experiment. Okay, so let us see the example first. Definition first. An experiment is defined as a process for which its result is well defined, and a deterministic experiment is an experiment whose outcomes can be predicted with certainty or under ideal conditions. And a random experiment is an experiment whose all possible outcomes are known in advance. So those whose each outcome is not possible to predict in advance and can be repeated under identical conditions are called as random experiment. Say for example, a die is rolled, a fair coin is tossed. These are simple examples for this random experiment. And a simple event or elementary event or sample point is the most basic possible outcome of a random experiment, and it cannot be decomposed further. So we call this as a simple event. And a sample space is the set of all possible outcomes of a random experiment. Okay, so each point in a sample space is an elementary event. Let us see a few illustrations. So if a die is rolled, then the sample space S will be equal to 1, 2, 3, 4, 5 and 6. As you already know, a die has only 6 faces. Okay, so the numbers mentioned on the sides of each face is considered as the sample space of this particular event. And a coin is tossed, then the sample space is said to be h comma t. So as you can see, a coin, if you take a coin, the coin has only two sides. So therefore only two faces. So therefore we have only two sample elements for this particular event. And suppose we toss a coin until a head is obtained, one cannot say in advance how many tosses will be required. And so the sample space is said to be S is equal to H TH, TTH, TTTH, and this continues, and it is said to be an infinite set. So the sample space associated with the number of passengers waiting to buy train tickets in the counter is said to be S is equal to 0, 1, 2 and so on. Okay, so 0, 1, 2 specifies that 0 specifies there are no number of passengers, 1 specifies there is one passenger waiting to buy a train ticket, and 2 denotes the two passengers waiting to buy the train tickets. So if the experiment consists of choosing a number randomly between 0 and 1, then the sample space is S is equal to X such that the range is from 0 to 1. Okay, so the range is from 0 to 1. And next, the sample space for the life length of t in hours of a tube light is given as t such that 0 strictly less than t strictly less than 1000. Okay, so this is just a condition that we are specifying. Okay, so these are certain illustration for a sample space. Okay, so now the number of sample points or the elementary events in a sample space can be divided into two. One will be the countable number of sample points, and the other one will be the uncountable number of sample points. Okay, so S is equal to X such that 0 strictly less than X strictly less than 1, and between 0 and 1 there are infinite number of samples, number elements. Okay, so therefore we say this is uncountable. Okay, so next, this countable number of sample points can also be divided into two groups. So one will be the finite number of sample points. Say for example, in the if you throw a die, you get the sample space to be equal to 6, right? So this is, we call this as a finite number of sample points. And the next one is nothing but countably infinite number of sample points. Say for example, any number of coins, when the coins are tossed, any number of coins are tossed, then the possible outcomes that we will get will be infinite. So we call this as countably infinite number of sample points. Okay, so now let's move to a finite sample space. So we'll see certain events associated with this finite sample space. Okay, so there are certain types of events like a sure event or certain event, complementary event, mutually exclusive event, equally likely events, impossible event, mutually exclusive events, exhaustive events, independent events. Okay, so we'll see about see these definitions and certain examples are related to it. So when the sample space is finite, any subset of the sample space is said to be an event. That is, all the elements of the power set P of S of the sample space are defined as events. So in general, an event is a collection of sample points or collection of elementary events. Okay, so a sample space S is called a sure event or a certain event. Then the null set phi in S is called a impossible event. And next, the next definition is about the complementary event. So for every event A, there corresponds another event A bar, and this is called as the complementary event of A. So it is also called as not A. So A bar we can also specify it as not A. Say for example, suppose a sample space S is given by S is equal to 1, 2, 3 and 4, and let the set of all possible subsets of S, the power set of S be P of S. So what will be the sample space here? So P of S is equal to the null set first, and then 1, 2, 3, 4, and then two elements in that particular set. Okay, so 1 comma 2, 1 comma 3, 1 comma 4, and then 2 comma 3, 2 comma 4 and 3 comma 4. Then we'll be having three elements in each set. So 1 comma 2 comma 3, 1 comma 2 comma 4 and 1 comma 3 comma 4 and 2 comma 3 comma 4, and finally we'll have all the four elements in the final set. Okay, so the collection of all these sets is said to be the power set of S. That is set of all possible subsets of the sample space. Okay. So we are having a certain observation, that is all the elements of P of S are called events, and phi is an impossible event. Okay, so this notation null value is said to be an impossible event, and this individual values, each set, if it is having only one outcome, possible outcome, then we say it is an simple event or elementary event. And 1, 2, 3, 4, if we have all the possible outcomes as the is equal to the set of sample space, then we call this as a sure event or certain event. So next, two events cannot occur simultaneously, and these if they cannot occur simultaneously, we call this as a mutually exclusive event. Okay, so A1, A2, A3 to AK are mutually exclusive, and it means that AI intersection AJ is equal to phi for I not equal to j. As you can see, intersection represents there are not any common elements in both AI and AJ. So therefore we get a null event. So this will be an impossible event. Okay, so this event is also called as mutually exclusive, and two events are mutually inclusive when they both can occur simultaneously. So they give a condition like AI intersection AJ is not equal to phi. That is, they do have certain elements in common. Okay, so that is the meaning of this particular equation. Say for example, so when we roll a die, the sample space S is equal to 1, 2, 3, 4, 5, 6. Okay, so from this particular sample space, so let us define these, what is an event, what is a mutually exclusive event and mutually inclusive event. So let us consider, since 1 comma 3 intersection 2 comma 4 comma 5 comma 6 is equal to 5, the events 1, 3 and 2, 4, 5, 6 are said to be mutually exclusive events, because we do not have any common elements in both these sets. So therefore we call this as a mutually exclusive events. And the events 1 comma 6 and 2 comma 3 comma 5 are mutually exclusive. Here also we do not have any common elements here between this set and this set, so they both are mutually exclusive. But in the next example, we have 2 comma 3 comma 5 comma 5 comma 3. So this is called mutually inclusive because we have one element in common in both these sets. Okay, so intersection of both the sets, we have one element in common, that is 5. So therefore this event is not equal to an empty set. So we call this as a mutually inclusive event. Okay. So when do we call the set of events as exhaustive? If the union of all the events is equal to the set of sample space, then we call this as exhaustive events. And suppose A1, A2, A3 to AK are mutually exclusive and exhaustive events. This is called mutually exclusive and exhaustive events if we have these two conditions, that is AI intersection AJ must be equal to phi, and A1 union A2 union A3 union AK is equal to yes. So when these conditions are satisfied, then we call these events as mutually exclusive and exhaustive events. Say for example, when a die is rolled, as we already know, the sample space would be 1, 2, 3, 4, 5 and 6. So some of the events are, they are specifying certain events like 2, 3, 1, 3, 5, 4, 6, 6 and 1, 5. So from this given subset, we have to find what is an exhaustive event and what is not exhaustive event, and which is mutually exclusive and exhaustive event. Okay, so since 2 comma 3 union 1 comma 3 comma 5 union 4 comma 6 is equal to 1 2 3 4 5 comma 6, the events are exhaustive events. So we call this, so we can see that all the numbers are present here. Okay, so we call this as exhaustive events. And similarly, 2, 3, 4, 6, 1, 5 are also exhaustive events because we have 1, 2, 3, 4, 5 and 6. All these elements of the sample space are present here. And then 1, 3, 5, 4, 6, 6 and 1, 5 are not exhaustive events because we have certain numbers missing in the from the sample space. Okay, so we don't have the number 2 here. Okay, so therefore we call this as not exhaustive event. And when do we say it is mutually exclusive and exhaustive events? When suppose 2 3 and 4 6 and 1 5, we do not have any common element in each set, and union of all these sets will be equal to the sample set S. So then we call this as a mutually exclusive and exhaustive events. So these are types of events which are associated with the sample space, and we can visualize this in terms of Venn diagrams. Say A and B are mutually exclusive in the sense there is no any common element between A and B. So therefore it is colored in separately. So it is disjoint. We do not have any connection here. So we call this as mutually exclusive. And if they are mutually inclusive, it means that we do have certain elements which are common to each set. Okay, so and the outer triangle denotes the set of sample space S. Okay, so next A and B are mutually exclusive and exhaustive. That is, they will be disjoint, but all the elements in set A and set B will be filled with the sample space, a set of elements of the sample space yes. Okay, so that is the meaning of this. If A and B are mutually inclusive and exhaustive, then we do have certain elements which are common between A and B, and the whole set A and B contains the set of sample elements. Okay, so this is a simple diagrammatic representation. So now let S be the sample space associated with a random experiment and A be an event. So let n of S and n of A be the number of elements of S and A respectively. So then the probability of the event A is defined as P of A is equal to n of A by n of S. So here n of A denotes the number of cases favorable to the set A, and n of S represents the exhaustive number of cases in the sample space S. So here we have a small figure where every probabilistic model involves an underlying process, and this is shown in the following figure. So first we conduct a random experiment, and based on this random experiment, we have a set of uh, elements, or we call this as a sample space S. And there is a collection of subsets from the particular sample space S, and we call it as event A, event B, or event C. And for based on this, we find the probability for each event, and we call this as event A. The probability of A would be P of A, and event B, the probability of B would be noted as P of B, and for event C, the probability of C would be P of C. Okay, so this is a simple procedure that we will be undertaking in this probabilistic model. So now we move to the axiomatic approach to probability. So let S be a finite sample space, and let P set be the class of events, or we call it as power set, and let P be a real valued function defined on P of S. Then P of A is called the probability function of the event A when the following axioms hold. So for any event A, P of A must be greater than or equal to 0. For any two mutually exclusive events, so P of A union B must be equal to P of A plus P of B. So we call this as the additivity axiom. And for certain event, P of S is equal to 1. And we call this as a normalization axiom. Okay, so we have to note that the P of A, probability of A varies from 0 to 1, and if A1, A2, A3 to AN are mutually exclusive events in a sample space S, then P of A1 union A2 union A3 to A union of AN is equal to, instead of this union symbol, we use the addition symbol here. Okay, so these are certain conditions for the axioms of probability. So now we'll see certain theorems for these finite probability spaces. So let S be a sample space, and for any subset A of S, let P of A is equal to N of A by N of S. So then P of A satisfies the axioms of probability P1, P2 and P3. Okay, so this is the one theorem that we are specifying here. And the next theorem would be, let S be a finite sample space. Say S is equal to A1, A2, A3, AN. So these are the elements in the given sample space. A finite probability space is obtained by assigning to each point AI in S a real number Pi, and this is called the probability of AI, satisfying the following properties. So each Pi must be greater than or equal to 0, and the sum of Pi is equal to 1. Okay, so that is summation of all the probabilities must be equal to 1. So if the probability P of A of an event A is defined as the sum of the probabilities of the points in A, then the function P of A satisfies the axioms of probability P1, P2 and P3. So let us see an example. So an integer is chosen at random from the first 10 positive integers, and we have to find the probability that it is an even number or it is a multiple of 3. So the sample space, as you can see, the first 10 positive integers is said to be the sample space here. Okay, so S is equal to 1 to 10. So the number of elements in the sample space S is equal to 10, and let A be the event of choosing an even number and B be the event of choosing an integer multiple of 3. So the first event, we have all the even numbers here. So there are totally 5 even numbers. So N of A is equal to 5, and the multiples of 3, we have 3 elements here, 3, 6 and 9. Okay, as you can check, 3 ones are 3, 3 twos are 6, 3 threes are 9, and 3 fours are, it becomes 12. So we do not have that number in the sample space. So we have only 3 elements here. So the probability of choosing an even integer, we have the formula. So N of A by N of S, which is equal to 5 by 10, which is equal to 1 by 2. and P of choosing an integer multiple of 3 is equal to T of B, which is equal to N of B by N of S, which is equal to 3 by 10. So now let's see some basic theorems on probability. Okay, so we have already used the formula called T of A union B is equal to T of A plus T of B. Okay, so the probability of an impossible event is 0. That is P of phi is equal to 0. Uh, Let us see the proof here. So the impossible event contains no sample point. So therefore, the sample space union an empty set will again be a sample space. So the probability of S union phi will be equal to probability of S, and P of S plus P of phi is equal to P of S. So as you can see, P of S gets cancelled. So P of phi is equal to 0. So next theorem would be, if A bar is the complementary event of A, then P of A bar is equal to 1 minus P of A. So as you can see in this particular exam figure, this is the sample space S, and in it we have a particular event A. Okay, so those events which do not contain belongs to this particular set A is said to be the complementary event A bar. So let us see the proof. So let S be a sample space. So we have A union A bar to be equal to S, and P of A union A bar is equal to P of S, and instead of union we use the addition symbol here. So P of A plus P of A bar is equal to P of S, and since A and A bar are mutually exclusive events, we equate P of S to be equal to 1. So we can see that P of A bar is equal to 1 minus P of A, or P of A is equal to 1 minus P of A bar. Okay, so this is the proof. So next we'll see the next theorem. So if A and B are any two events and B bar is the complementary events of B, then P of A intersection B bar is equal to P of A minus P of A intersection B. So clearly from the figure we can see that this is a sample space S, and this is A here, and this is B, set B. Okay, so A intersection B is the middle area here, as you can see, and A intersection B bar, those elements which do not contain the elements of B. So therefore we write it like this. Okay, so it is clear from the figure that A intersection B bar union A intersection B is nothing but the set A. Okay, so we find the probability of this particular event now is equal to P of A. So P of A intersection B bar plus P of A intersection B is equal to P of A. Okay, so as you can see, we use the addition symbol here instead of union. So since both are mutually exclusive event, we say that P of A intersection B bar, we take this to the right hand side. So we have P of A minus P of A intersection B. So next we move to the addition theorem on probability. So if A and B are any two events, then P of A union B is equal to P of A plus P of B minus P of A intersection B. So as you can see, this is the sample space S, and in it we have B and we have A intersection B bar. Okay, so those elements which do not belong to B. Okay, an intersection of A intersection B bar. So from the diagram we have A union B is equal to A intersection B bar union B. As you can see, A union B is nothing but A intersection B bar union B. So P of A union B is equal to P of A intersection B bar union B. And next we use the addition symbol here. Okay, and since both these are mutually exclusive events, and from the previous theorem we have we substitute instead of A intersection B bar, we substitute P of A minus P of A intersection B plus P of B. Okay, and then therefore we have P of A union B is equal to P of A plus P of B minus P of A intersection B. So we'll see an example. So given that P of A is equal to 0.52, P of B is equal to 0.43, and the intersection of A and B will be equal to 0.24. So this is the data given. So we have to find P of A intersection B bar. We use the particular formula and we find 0.28 to be the solution of the first subdivision. And P of A union B, we substitute the formula and similarly we get 0.71, and P of A bar intersection B bar is nothing but the union of the whole bar. Okay, so therefore we get P of A union B the whole bar, which is equal to 1 minus, this is a complementary event, right? So we already know the formula for complementary event. So P of A is equal to 1 minus P of A bar. So P of A bar is equal to 1 minus P of A. So we get 1 minus P of A union B here. So we have the formula. So the solution will be 0.29. And similarly, P of A bar union B bar is nothing but 1 minus P of A intersection B. Okay, so the opposite of complement that we use here. Okay, so I hope you can understand this example. So next we move to the conditional probability. So consider the following example to understand the concept of conditional probability. So suppose a fair die is rolled once, then the sample space is S is equal to 1, 2, 3, 4, 5, 6. So now we ask two questions. One is, what is the probability of getting an odd number which is greater than 2? And Q2, if the die shows an odd number, then what is the probability that it is greater than 2? So the first case would be the event of getting an odd number which is greater than 2 is 3 by 4. So let P1 be the probability of getting an odd number which is greater than 2. So therefore P1 is equal to n of 3 comma 5. Okay, so divided by the total number of sample space, which is equal to 2 by 6, and simplifying, cancelling the terms, we get 1 by 3. And the case 2 is nothing but, if the die shows an odd number, it means we restrict our sample space S to a subset containing only odd number. That is, S1 is equal to 1 comma 3 comma 5. So then our interest is to find the probability of the event getting an odd number greater than 2. So let it be P2. So P2 is equal to n of 3 comma 5 by n of 1 comma 3 comma 5, which is equal to 2 by 3. Okay, so in the above two cases, the favorable events are the same, but the number of exhaustive outcomes are said to be different. So in case 2, we observe that we have first imposed a condition on the sample space and then asked to find the probability. So this type of probability is called a conditional probability. So this can be written by using the sample space as P2 is equal to the case 1 divided by the next case, which is equal to 2 by 6 by 3 by 6, which is equal to 2 by 3. Okay, so sample space is same for probability and the conditional probability. So let us see a formal definition here. So the conditional probability of an event B, assuming that the event A has already happened, is denoted by P of B or A, and it is defined as P of B by A is equal to P of A intersection B divided by P of A, provided P of A is not equal to 0. And similarly, we have the formula for P of A divided by B. And rewriting the definition of conditional probability, we get the multiplication theorem. That is, P of A intersection B is equal to P of A by B into P of B. So the previous formula, what we do is we take the P of A to the left hand side. So we get P of A intersection B is equal to P of B by A into P of A. So that is how we get the multiplication theorem on probability. And next we move to the independent events. So the events are said to be independent if the occurrence or non-occurrence of any one of the event does not affect the probability of occurrence or non-occurrence of the other events. So two events A and B are said to be independent if and only if P of A intersection B is equal to P of A into P of B. Okay, so next we move to the total probability of an event. So I'll just explain the theorem statement alone. So if A1, A2, A3 to AN are mutually exclusive and exhaustive events and B is any event in S, then P of B is called the total probability of event B, and P of B is equal to P of A1 into P of B by A1 plus P of A2 into P of B by A2. The summation of all these terms will be written as I varies from 1 to n. So probability of AI plus probability of B by AI. So this is a simple proof it is given, and based on the given theorem, we'll see one example. So a factory has two machines 1 and 2. So machine 1 produces 40% of the items of the input output, and machine 2 produces 60% of the items. Further, 4% of items produced by machine 1 are defective and 5% produced by machine 2 are defective. So if an item is drawn at random, find the probability that it is a defective item. So we say A1 to be the event that the items are produced by machine 1, and A to be the event that the items are produced by machine 2, and let B be the event of drawing an effective item. So we have to find the total probability of event B. Okay, so we can see that A1 and A2 are mutually exclusive and exhaustive events. So we give the formula here. So we have, based on the given formula, P of A1 is equal to 0.40. Since it is 44%, 40%, we specify divided by 100, so we get 0.40, and P of B by A1 is equal to 0.04. So it is given, all this is also given. Okay, so out of A1, 4% is defective, so we specify it as 0.04. And similarly for P of A2 and P of B by A2, the values are given and you substitute it in the given formula. So we get 0.046. So let us see the summary of what of this lecture. So we saw about the sample spaces, the axioms of probability, and definitions about impossible event, complementary events, and conditional probability and independent events, and about total probability. So thank you for listening. This will be the end of my lecture. So thank you for listening.